This tutorial will show you how to use muscle stiffness to maintain limb position against perturbations. We'll build a simple two-segment arm with two muscles controlling the motion around the elbow joint. Begin by creating a new project. You can find a copy of this project located at C, Program Files, AnimatLab, Tutorials, Examples. Please choose where you want to save this project and name it Limb Stiffness. Once the project is created, add a new organism and name it Arm. Also, this project will use masses and forces within the kilogram and newton range, so we need to set the mass units for this project to be kilograms. Once we do this, we need to reset the values on the mouse spring to be in the range useful to us. Set the spring damping to be 10 kilograms per second and the stiffness to be 100 newtons per meter. Now open the body editor and add a new box. Name it Humerus. This will be our upper arm bone. Set its density to 1 gram per cubic centimeter and change its size to be 40, 5, and 5 centimeters. Now add a new box with a hinge joint. Name it ulna. This will be our lower arm bone. Set its density to be 1.67 grams per cubic centimeter. Change its color to blue. Set its size to be 5, 40, and 4.5 centimeters. Change its rotation to 0 and its local location to 0, negative 18.5, and negative 16 centimeters. We also need to go back and freeze the humerus so it remains locked in place. Now select the joint and name it elbow. Set its local X to be 0 and local Z to be 16 centimeters. Rotate it around the y-axis by negative 90 degrees and change its maximum limit to 75 and minimum to negative 75 degrees. Now we need to add some attachment points for our muscles. Add an attachment and change its name to bicep-humerus. Set its location to 0, 15, and negative 2.5 centimeters. Add another attachment on the other side and name it triceps-humerus. Set its location to be 0, 15, and 2.5 centimeters. Now add an attachment to the ulna and name it bicep-ulna. Set its location to 0, 0, and 12 centimeters. Add an attachment on the other side of the ulna and name it tricep-ulna. Set its location to 0, 0, and 20 centimeters. When we add our muscles, they'll be symmetrically located 4 centimeters away from the joint on either side. Now let's add our bicep muscle to the humerus. Name it bicep. One of the trickiest parts of using muscles is configuring the properties correctly so they produce realistic biological results. Of course, if you're modeling a specific muscle and you've done the measurements on that muscle, you can use your experimental data to configure your models. For this tutorial, we'll just use a few heuristic rules to come up with the values for the muscles. First, we know that the mass of the ulna is 1.5 kilograms. This means that gravity will apply a force of almost 15 newtons at the center of mass of the ulna. Since our muscle is attached much closer to the center of rotation, it will need to apply around 60 newtons of force in order to balance the force applied by gravity. Also, muscles rarely contract more than 40% of their resting length. Our muscle will have a resting length of around 33 centimeters. So if we assume that we can contract it by 40%, this is 13 centimeters. If we use a SE spring constant of 1 kilonewton per meter, then when it's extended by 13 centimeters, it will produce 130 newtons of force. This is a little over double what we need to counteract the weight of the arm, so this will do for now. The parallel spring is usually smaller than the serial spring. We know that the maximum length the muscle will ever be stretched is 4 centimeters if it's fully extended to 90 degrees. For now, let's assume that the spring constant for our PE spring is 200 newtons per meter. Under this case, we would get a tension of around 8 newtons with a full extension. Finally, we need to know what the dampening needs to be. A good rule of thumb is that the maximum velocity of shortening of a muscle is usually never greater than 2 times the resting length per second. In this case, that would be 67 centimeters per second, and the maximum amount the muscle can extend is 8 centimeters. So at that velocity, it can cover 8 centimeters in a little more than 0.1 seconds. If we use this and the spring constants, we can calculate that our dampening coefficient needs to be 120 newton seconds per meter. Now let's use these values in our muscle model. Set the SE spring constant to 1 kilonewton per meter, the PE spring constant to 0.2 kilonewton per meter, and the dampening coefficient to be 120. Next, we need to string our muscle between the attachment points. Select the attachment property and add the bicep, humerus, and ulna attachments. Now our muscle is drawn as a red line between those attachments, and the muscle length was calculated for us. The calculated length was also used to set the resting length of the muscle. Change the L width parameter to be 10 centimeters. This controls the length tension curve, or how much the tension drops off as the length changes. The next thing we need to configure is the stimulus tension curve. This function translates the membrane voltage of a neuron into an active tension that's applied to the contractile portion of the muscle. The neuron acts like the membrane of the muscle to integrate incoming spikes and generate muscle tension. The first part of this example will use the firing rate neurons. They don't explicitly model resting potential for the neurons, so we need to move the range of our function. Change the amplitude to 1 kilonewton, steepness to 150, and X offset to 60 millivolts. Then set the lower limit to be 0 and the upper limit to be 100 millivolts. Set the upper output value to be 1 kilonewtons. Now the membrane voltage of the neuron between 0 and 100 millivolts will produce a corresponding active tension that's controlled by this function. Next, copy this muscle and paste a new one onto the humerus. Change its name to be tricep. Add its attachments. And set its L width to be 10 centimeters. Its stimulus tension properties are the same. Finally, change its color to be green. Now we need to add a new line chart. Add items to view the tension and length of our muscle, and an item to view the elbow rotation angle. Notice that all of the muscle values are color-coded using the color of the muscle to make it easier to see what's happening with them. Go back and label the axes. Also, set the auto scale property of the elbow angle to be min-max. This means we'll manually specify the axis values. Set the max to be 0.5 and the min to be negative 0.5. Set the update interval to 500 milliseconds and the collect time window to 5 seconds. Finally, set the camera offset to 75 centimeters and the rotation to negative 90 degrees. Now run the simulation. Our arm immediately falls down and stays there, but this is good in this situation. If you put your own arm out at 90 degrees and then consciously quit holding it there, your arm also swings down like this. This means that the springs and damping we're using aren't totally unreasonable. For example, if your damping or spring constants were too large, it could cause the weight to slowly oscillate down instead of falling rapidly. However, to make things easier for the first part of this tutorial, we'll disable gravity. You can do this by setting the gravity value to be 0 in the environment of the project workspace. Run the simulation again. This time the arm stays in place. Also, notice that if you disturb the arm by pulling on it with the mouse spring, it returns to its equilibrium position. This is caused by the passive properties of the muscle. When you pull on the muscle, it generates a passive tension that attempts to restore it to its resting position. However, if you only use passive properties, you can't change the equilibrium point to different joint angles. To do this, you need to actively generate tensions on the two muscles that cause the arm to balance at a desired location. So let's stimulate our muscles to generate some active tensions. Open the behavioral editor and add two muscle nodes. Name the first bicep and the second tricep. Set their muscle IDs to the corresponding muscle. Next, add two normal neurons. Name the first NBMN for normal bicep motor neuron. Name the second NTMN. Draw a connection from the normal neuron to the muscle. This adds an adapter between the two nodes. Change the source data type for each to be membrane voltage and leave the gain function as the default. This will directly transfer the membrane voltage of the neuron to the muscle. Now we need to know how much to stimulate our neurons in order to produce a specific tension. This is actually a rather complicated procedure that requires you to use the inverse of the functions that the muscle uses to calculate the forces. A detailed description of this process can be found on the muscle help page. However, to make things easier, the muscle has a property called Calculate Stimulus. When you click on this property, it opens a dialog where you can enter the tension you want the muscle to generate and the offset of the muscle length from its resting length. When you hit the Calculate button, it will use the current settings of this muscle to calculate a number of values. Among them is the membrane voltage stimulus that's needed to produce the desired tension. Let's have both of our muscles generate 20 newtons. That force requires a voltage stimulus of 35.3 millivolts. Our normal neurons have a membrane conductance of 100 nanosiemens, so if we inject a current of 3.53 nanoamps, it will produce the voltage we need. Go back and add a tonic current stimulus to each of our neurons. Change their names to bicep or tricep stim A. Change them to always be active and set their amplitude to 3.53 nanoamps. Now let's add a motor stimulus to the elbow joint. The purpose of this stimulus is to let the muscles have a little time to reach their steady state values. Change its name to steady arm and set the end time to 1 second. Also, it's important that you set the disable when done property to true. This will disable the motor after 1 second so that all the torques are caused by the muscles from that point on. Run the simulation. Again, if we deflect the limb, it returns to its equilibrium point. However, this time you can see that each muscle is actively generating 20 newtons of force as we predicted. Unlike before though, we have the ability to set the equilibrium point of the arm to any joint angle we want. We can use the stiffness of the two muscles to control this. Go back to the stimulus for the bicep and increase it slightly to 3.6 nanoamps. This will make the tension of the bicep a little larger and shift the set point towards a more flexed position. This time the arm is more flexed, and if you disturb it, the arm goes back to the new set point and not the one we originally had. By adjusting the tensions of each of the muscles, you can move the set point to any position you want. Go back and set the stimulus current so that the two muscles are balanced. Now what do you think will happen when we turn gravity back on? Let's go ahead and try it and see. Set the gravity back to negative 9.81 meters per second squared and run the simulation. This time our set points were destroyed. The arm no longer maintains its position and it just falls down like it did when we originally started. So what caused this? The reason this happened is that now gravity also causes a torque around the elbow that tries to extend the arm. The 20 newtons of tension are not enough to counter the force caused by gravity. This will require something closer to 60 newtons of force. In addition, we'll also need 20 newtons of extra force to use our muscle stiffness to control joint position. So the force for the bicep needs to be around 80 newtons, and the force for the tricep needs to be 20 newtons. Go back and calculate the voltage required to generate 76 newtons of tension. This will require a current of 4.47 nanoamps. Now let's run the simulation again. This time the arm doesn't just fall down, and we get a new set point that's very extended because we're using less than 80 newtons of force. Go back and increase the current to 4.5 nanoamps. This time we get a set point that's slightly flexed. Now let's move on to some more biologically realistic examples. Go back and disable the adapters and stimuli that we've added. Then add two non-spiking neurons. Name the first one SBMN and the second STMN. Set the resting potentials to be negative 100 millivolts and their time constants to 100 milliseconds. These neurons will represent the membrane of our muscle and will integrate the spikes coming from other neurons in the system to cause contractions in the muscle. Draw connections from the neurons to the muscles. We'll use the default settings for the adapters. Next, we need to go back and reconfigure our stimulus tension curves to use these neurons instead of the firing rate models. Set the X offset to be negative 40 millivolts, lower limit as negative 100 millivolt, and upper limit as 0 millivolt. Do this for both muscles. Now, since we've changed the properties of a muscle, we need to recalculate the voltage stimulations that we'll need. Add two new tonic current stimuli to the non-spiking neurons. We'll use them to control the set points first before moving on to the more difficult spiking neurons. Set these stimuli up the same way we've been doing. Our tension calculations have shown us what membrane voltages we need. A bicep current of 45.2 nanoamps and a tricep current of 36 nanoamps will produce the voltages needed. Add a new axis to the chart to view the membrane voltages of our two neurons. Set the collect data interval to 10 milliseconds. Now let's move on and use spiking neurons. Go back and disable the stimuli we added. Then add two spiking neurons. Call the first bicep activate and the second tricep activate. Add a tonic current stimulus to each of these neurons. Configure them as before and leave their currents at 10 nanoamps. Now add the bicep activate to the chart and set the auto collect data interval to be true so we can see any spikes that occur. When we run the simulation, you can see that 10 nanoamps isn't sufficient to produce firing in the neuron because we can't depolarize it enough. Let's up the current to 20 nanoamps and try again. Again, nothing. Ramp it on up to 30 nanoamps. This time we get firing, but it's high frequency. The problem with this is that we really want to be able to start at a low firing frequency of around 10 Hz and gradually ramp up by slightly increasing the current. But we had a gap where it didn't even produce firing from 0 to 30 nanoamps, and then we got a high firing frequency rate. We can fix this by changing a few of the parameters of the neuron. First, increase the after-hyperpolarization time constant of the neuron to 60 milliseconds. This will increase the refractory period of the neuron and slow down the firing frequency. Then decrease the threshold voltage to -58 millivolts. This lowers the bar and allows even small depolarizing currents to produce firing in the neuron, and larger currents produce increasing firing frequencies. Now reset the current back to 10 nanoamps and rerun the simulation. This time we get a frequency of around 16 Hz. This is good enough. Connect the spiking neurons to the non-spiking neurons using a nicotinic acetylcholine synapse. Now set the bicep current to 80 nanoamps and the tricep current to 66 nanoamps and run the simulation. Now, even though we're using spiking neurons, we still get a similar equilibrium set point. One important thing about using equilibrium set points is that you can use them to move the arm to new locations simply by adjusting the set point. Let's do that now by adding a new stimulus to the bicep control neuron. Set it to end at 40 seconds. Start at 20 seconds. And have a current of -0.5 nanoamps. This will slightly reduce the tension of the bicep, causing it to extend. Now our arm moves from one set point to another and back again simply by changing the input current to a neuron. By adjusting the firing of either of our spiking neurons, we could make the arm move to any position we wanted. However, you should keep in mind that this method isn't generally used by the nervous system to really move your arm. The main reason is because it's so slow. It takes seconds to move from one set point to the next, but you can move your arm much faster than this. Your nervous system actually uses a more complex 3-burst pattern to rapidly move the arm between new locations. Equilibrium points like this are mainly used for maintaining the position of the arm against disturbances. This tutorial has shown you how to use muscle stiffness to position an arm at any location using equilibrium set points, and how to move between these set points using neural control.